V to this. So it's an operator. It's telling you to do something, but it involves differentials. So it's just a differential operator. Okay? Now let's symbolize that operator by capital letter L. Okay. So effectively, we can rewrite this equation now in the following form: LU equals EU. Now, so L's your differential operator. It's just this, okay? Times some function that depends on space, on x, equals a constant times the same function. So yeah, u. Now, if you get an equation in that form, it's generally referred to as an Eigen equation. Now, Eigen is a German word, because this analysis, I assume, I'm a little bit weak on the history of mathematics. I'm much stronger in the history of physics, as you probably noticed. So I assume some Germans invented this for the first time, and so they talked about this Eigen equation. The word Eigen, now I speak German, but my mathematical history is a bit weak. Eigen in German simply means own, like O-W-N, or self. Okay. So an equation of this form is called an Eigen equation, and there are more terms. This U here, that's called an Eigen function, right? So the U here, it's the same function, both sides, is called the Eigen function, and this constant here, this one, is called the Eigen value, right? So an Eigen equation, typically of this form, some kind of operator, L, times the Eigen function equals a constant called the Eigen value times the Eigen function again. So in other words, what you're doing is you're taking this function here on the left-hand side, you're operating on it somehow. You're doing something with it, with this L. This L's telling you to do something with this function. But what's interesting is the result that you get is just the same function, but stretched or compressed. This is just a constant, it's just a number, right? I'll say that again in different words. So with an Eigen equation, you take some function, you operate on it, and the result you get is the same function. It's not changed, except its size might have got longer or shorter or bigger or smaller by a factor e. Right? So Eigen function, Eigen value, and that's your operator. Now, the really interesting thing to come out of all this came out of the Schrödinger equation. Now, well, two things I can say. Often, now we will solve this Eigen equation, and what's interesting about Eigen equations is quite often these Eigen equations will only have a solution when E, the constant here, has particular discrete, not continuous. I mean, it may have continuous values, but quite often this equation will only have solutions when the eigenvalue here takes on discrete values. And you're probably going, that's the essence of quantum mechanics, right? Quantized physical values, physical quantities, or as they're usually called technically, observables. Remember, a quantum mechanical observable is just some physical quantity that you can measure, right? Like mass and position and momentum and charge and spin and all those things, angular momentum, whatever. Right? So that's in mathematical terms. That's characteristic of an Eigen equation. Often there's to get a solution, you're trying to solve for U here. You're trying to find what is the Eigen function, and this Eigen equation may, under certain circumstances, only have a solution when these constants here, the E, take on discrete values. So out of the Eigen equation, you're getting the core nature of quantum mechanics. In other words, discrete physical values, observables that have discrete values and nothing in between. Okay. Now, there's another thing I could mention. Maybe I'll put it here. This Schrödinger equation, which is an Eigen equation, is linear. Now, what do I mean by that? Well, L of psi 1 plus psi 2 is equal to L psi 1 plus L psi 2. Okay? If your operator here, your differential operator here, L, if it has the following property, that if you take the sum, if you take two wave functions, psi 1 plus psi 2, you add them together, and then you apply the operator L to it, if the result is just the same as applying the operator L to psi 1 separately, and then adding the result of applying L to psi 2 separately, and then adding those two results, L psi 1 plus L psi 2, if the right hand side is equal to the left hand side, then that equation, that L if you like, is said to be linear. And Schrödinger's equation is linear. And you may say, so what? Well, if Schrödinger's equation is linear, like this, it means that you can add psi functions. That's usually called superposition. Remember, in an earlier session, one of the characteristics of quantum mechanics is that you can take two states. You can look on this as a state, a description of the physical system. That's what a state is. You can take two states and add them and get another state, and that third state, the result of the addition, is also a state for your quantum system. So quantum mechanics allows superposition, in other words, adding states. And now in mathematical terms, that's easily seen, because our Schrödinger equation produces Eigen Equations, like this. Okay? So from Schrödinger equation, we have, in a sense, deduced two basic properties of the nature of quantum mechanics. One is quantization. In other words, this Eigen equation will often only have solutions when this constant here takes on discrete values, and not values between those discrete values. Like, imagine this is allowed constant and this one's allowed constant. Then anything in between, not allowed. There will be no solution for those values. Only certain discrete values are allowed. Okay, so the Schrödinger equation gives you quantized values of physical quantities, of observables, right? And the other thing is linearity. In other words, superposition. The Schrödinger equation is linear. It has this form, and therefore superposition. You can add states. You can add psi functions. Okay, because the equation is linear, and superposition, or adding states, same thing, is essential. It's like one of the basics of quantum mechanics, and if you think about it, one of the most mysterious in terms of interpretation. Physically, what does that mean? What does the Americans say? It fries your brain, right? It's, when you really start trying to think about what does superposition mean in physical terms, as a physicist, it's a tough one, a very tough one. Okay, and now in my view, the two characteristics of quantum mechanics I find the most mysterious. One is superposition, doing this, and the other one is entanglement. I won't be talking much about entanglement at this level, at senior level, undergrad level. a little bit on multi-particle systems, but entanglement is truly weird. I talked a little bit about it. Yeah, you know, the idea you have two particles, photons, whatever. They interact, they entangle somehow, and somehow become one system, and then they separate, maybe huge distances, and then if you perform a measurement on one, that will influence instantaneously, in zero time, the outcome of a measurement you perform on the second particle that's hugely far away. So you have what Einstein called spooky action at a distance, right? Spukhafte Fernwirkung, the famous German expression by Einstein. Spooky action at a distance. Non-locality, that's what the physicists refer to this phenomenon as, and the quantum computer people who use this phenomenon as the basis of quantum computing, which is ironic, they tend to call the same phenomenon non-locality as entanglement. Okay, so that second thing, entanglement or non-locality, for me is the second truly weird phenomenon in quantum mechanics. Right, now the next, I ran out of board, but the next thing to discuss is what is this constant, this E, and why choose the letter E for this constant? I mean, I could have said C or K or anything, right? Well, it turns out this E has properties of energy, and I'll talk about that in the next session. So, yeah, run out of board, and stay tuned. I really hope soon that you'll be seeing this whiteboard in clear, high definition. That's the plan. I'll be very disappointed if it doesn't work out, but we're doing trials, friend and I, and it's looking promising. So fingers crossed.